So welcome to the solution of problem 2-3. Here we will try to find a sum expression of the expected excess lifetimes in terms of the survival probabilities. So just before we begin, probably it's nice to get some definitions going. So I'll just remove this part where we describe the goal of the exercise and replace it with some definitions instead. What we want to find is the mean of something given something else. So for that, it's a good idea to recall the definition of conditional expectation, where we have from the book that the mean of g of n, given that n belongs to some event A, some set A, is equal to 1 over the probability of n belonging to A multiplied by the mean of g of n evaluated on only the set where n belongs to A. So that is the definition of conditional expectation. Now, what is the definition of just expected value of some function of n, f of n, for example? Let us also write that up. Well, that is the sum of each of the values that f of n can attain multiplied by the probability that f of n attains that value, which is the probability that n is equal to little n, where n ranges from 0 all the way up to infinity. And then also, we can see that there's a little bit more knowledge that we receive from the book, in the sense that it tells us, hint, we have that the sum of a to the n for n going from 0 all the way up to infinity is equal to 1 over 1 minus a, as long as a is numeric, has absolute value less than 1. And this is what we call a geometric series. So write this into your collection of formulas. It's good to have. And now we're ready to start solving the problem. So we start with this expression, expected value of n minus d given n greater than equal to d. Just for formality's sake, you can also write let d greater than equal to 0 be an integer. Like, this kind of stuff is really important in analysis 0. In this course, it's kind of depending on how much you want to go into details, but you can write this if you want. It's also okay if you don't. So we want to find the expected value of n minus d given that n is greater than equal to d. So for that, we use the definition of conditional expected value. So we need 1 over the probability of the event we condition on, which is n greater than equal to d. And then we want to multiply this with the mean of the event we're interested in, restricted to the set that we condition on, so restricted to n being greater than equal to d. So the mean of n minus d multiplied by an indicator function. So the 1 over the probability that n is greater than equal to d, it can just kind of rest out here on its own. And then we use the definition of expected value for an expression of n. That tells us that this expected value evaluates to the sum of n minus d multiplied by the indicator that n is greater than equal to d of n, multiplied by the probability that big N has value little n for n going from 0 up to infinity. So when we plug this part into the sum expression, we just take all of the capital N's and replace them with the small n's. And now we want to calculate this sum. And how do we do that? Well, first of all, we can try and see if we can try to remove this indicator function in some way. And the way we can do that is by moving it into the bounds of the sum. So each term inside this sum will only be different from 0 if n is greater than equal to d. So for n equal to 0, if d is 10, for example, then for n equal to 0, 1, 2, 3, 4, up to 9, then the entire term here will just evaluate to 0 based on the fact that 0 is not greater than equal to 10, 1 is not greater than equal to 10, etc., etc. So the only terms that actually have a positive value in this sum are the terms where n is greater than equal to d, which means that we can write a completely equivalent sum up by summing from d to infinity instead of from 0 to infinity. And since we've taken the indicator function into account by doing this, that means we can just remove the indicator function from our sum expression. And then what we have is this. Now another thing, if we think about what the hint tells us, it tells us something about a sum for n going from 0 up to something. Well, since the hint tells us that, then maybe we could consider the fact that we can use that in some way, which means it could be nice if we sum in the same way as they do over here. Over here they sum from 0 up to infinity. So let's try to sum from 0 up to infinity instead of summing from d up to infinity. So what should we do if we want to sum from 0 up to infinity? Well, the thing that happens when we do that is if we want to change the index down here, then we need to change the content of the sum accordingly. So if n is equal to d, then if n is equal to d up here, then this term is equal to 0, right? And if n is equal to d plus 1, then this term is equal to d plus 1 minus d, which is 1. So all in all, if I want to change the index from starting in d to starting in 0, I still need to make sure that the first term is 0, the second term is 1 for this part. So this is just equal to d. It corresponds to the fact that since I'm starting in a value that is d less than before, then I no longer have the need to subtract the d up here. Well, how about this then? Well, here, for n equal to d, the first term is the probability of n being equal to d. So down here, what I actually need is the probability of n being equal to n plus d, so that I still have that the first term gives me d here. So this is how I change the index from n equal d to infinity over to the indexation n equals to 0 to infinity. And why is it this can prove useful? Well, now we are essentially in a place that looks kind of like something that we've already seen in the book, right? So what did they do in the book? In the book they said, let's take this n and turn it into a sum of ones for m ranging from 1 up to infinity, right? But let's take a look at, does this actually remind of what we have in the book? Well, in the book, we can see that we need a 1 over here, but we have a 0. But why does it work out anyways? Well, the same thing is, when n is equal to 0, this entire term just vanishes. So it doesn't really make a difference if I sum from 1 or if I sum from 0. So I can just choose to sum from 1. And then I can replace this n here with the summation from m equal to 1 up to n. So I just say each n is equal to 1 added to itself n times. So what do I get? Then what I get is the sum for n equal to 1 up to infinity over the sum for m equal to 1 up to n over the probability of n being equal to n plus d. And we can use the trick that they also use in the book and interchange the order of summation. And we use this formula over here. If you don't know how this formula came to exist, then look at the first video. So what we can do is we can interchange the order of the summation. So we have index m in the outer sum and index n in the inner sum, as long as we also change the boundaries accordingly. And here I have the probability that n is equal to n plus d. And I can kind of see this term doesn't rely on m, so it's quite okay if I just evaluate the inner sum for itself already. And, well, what do I have? I have the probability that n is greater than or equal to d in the denominator. And in the numerator, I have the sum for m going from 1 to infinity. And for each m, the value of the inner sum is equal to the probability of n being equal to m plus d, plus the probability that n is equal to m plus d plus 1, and so on, up to infinity. So the inner sum evaluates to the probability that n is greater than or equal to m plus d. And this is what we can call the corresponding version for the conditional case compared to this result that we got in the book. Now, some people might prefer to sum from m equal to 1 up to infinity and have m plus d up here. Some other people might prefer to say, well, what I prefer is to sum the probabilities of n greater than or equal to m and instead have m ranging from, well, we still need the first value to be 1 plus d, so we let m range from 1 plus d up to infinity. So both of these kind of work because they are actually just two expressions for the same thing. So this is the answer, and this is the answer.